Hello. So, we could get started by if you guys have any questions, we could go over those first, or we could go over like any worksheet from Moira Jones practice problems. If you guys have any questions first.
Could we go over the Diels-Alder by chance?
Yeah. Do you want to go over the whole concept, or do you want to go over the practice problems from the Diels-Alder worksheet here?
Maybe if we just do some practice.
Uh-huh. Yeah, let's do that. Let's see. Let's go workshop 10. Let's send a copy. Okay. So let's see. Page. So this. Okay, so for this Diels-Alder here, we have our Diene, which is this highlighted part over here, and our Dienophile, right? So when we figure out our Diene and the Dienophile, I like to draw the pocket between the carbons that are going to make a new bond with each other, which are these carbons here. The other thing that I like to do is I like to number this 1, 2, 3, 4, 5, 6. And I know that these groups here of the diene are in groups because they are forcing in towards the pocket that I made there, right? So we know that these groups here on the dienophile are EWGs, electron withdrawing groups, because that atom directly attached to the dienophile is partially positive, right? And do you guys remember in the Endo rule, are the in groups cis or trans to the EWGs for Diels-Alder?
Isn't it trans?
Yep, it's trans. So in this case, right here, the negative charges and positive charges do align because they're all symmetrical, which means that we don't have to flip anything. We could just react it as it is, where the arrows of the mechanism are going to be these three arrows here. And that's going to give us this Diels-Alder product, where this is atom 1, 2, 3, 4, 5, 6. And we see between atoms 1 and 4, there's this CH2 group between them, where we could make that as a wedge bond like that, where this carbon here, I'm gonna highlight that, let's say blue, is that carbon right there. That is CH2, right? And since I made these wedges, the EWGs would have to be dashes because we said that they have to be trans to the in groups, right? These could be enantiomers as well because this ring here could have been a dash and these groups here could have been wedges. Another representation of that could be something like this. See, it's kind of hard to draw this going down. Right? Where this is atom 1, 2, 3. Wait, no. This is 1, 2, 3, 4, 5, 6. Where between 1 and 4, we see that CH2 between them. So this is a bicyclic ring, meaning that there are two rings in that product. Right? Any questions on this one?
Nope.
Okay. So, do you guys want to move on to the next ones, or do you guys have any other questions first? If not, we can go on like with this practice worksheet here.
I have a question, but this is
Okay.
regarding like Leibniz's chapter 14.
Yeah. Um, chapter 14 practice worksheet.
Yeah.
Yeah. Let's see. I don't think I have access to that. Can you, let's see, DM me on Instagram on that problem? I can see
Oh,
here.
I don't, what's it called? I lost my Instagram right now, so I can't
Oh,
send it to you. I could
I
probably
see.
send.
You
Wait.
could email it to me instead.
All right. Let
Yeah.
me do that.
Yeah.
Let me see.
Mhm.
Can you send, what's the email that I sent it to?
Yeah. I will put it in the Zoom chat.
All right.
And after that, I will go give you guys challenging Diels-Alder problems where it's not easy to find where the Diene is, like how it was in this example, and where the Diene file is, where we have to like rotate the bonds. Because we know in Diels-Alder, we want the Diene to be in the S-cis configuration, but sometimes in the problem, they give it to you in the S-trans configuration, which would not react. We have to rotate that single bond um, between the Diene to make the S-cis configuration and then react with the Diels-Alder. And there's also other considerations as well, such as like the EDGs, EWGs, and the partial charges have to align. If they don't align, we have to flip one of the groups. And I'll go over those examples as well.
Okay, I sent it over.
Okay, let me see. Let's see. Okay, let's see PDF. That's the conjugated alkenes. Okay, yeah. Which problem did you have a question on?
It was over D.
D. Okay. So for D, we have this conjugated system reacting with HBr excess in cold conditions. Okay. So in this example here, we have two alkenes that could react with this HBr here.
Mhm.
In cold conditions, we know that we are going to look for the kinetic product, which is the more stable carbocation intermediate. Let's look at this alkene first. We know that this carbon here is going to be the one that's going to get the carbocation. So we have to grab the hydrogen on the other side. So let's see what that would look like first. Wait, let's say we have that carbocation there. And let's draw its resonance structure. Which is going to give us that carbocation right there. Okay. It could have also reacted with the other alkene, which let's say we did react that with the other alkene. We want this carbon here to have the carbocation because that carbon there is allylic, which would give us this resonance set here. Let's see. Positive charge. And in this case, we could also do resonance by moving that double bond there to give us this resonance structure here. Positive charge there. Okay, once we have our two resonance structures, we have to choose the one that has the more stable carbocations. And do you know which one would that be and which one do we have to eliminate?
It would be the first one because we have two secondaries.
Right, two secondary allylic ones, where the second one has one secondary and one primary. So let's ignore this second set and let's just focus on these sets here. Right. So we know that the Br minus is just going to come back in and attack that carbocation. So let's say like we have Br minus, with two of them, one of them is going to attack there, another one's going to attack there, which is going to give us that product. And this product here, right? They are both secondary allylic, so they have like the same intermediate carbocation stability, right? Where now from here, we have excess HBr. So we could bring in another HBr because we have another alkene to react this with. HBr. HBr. Okay, this is a tricky one. Let's see. Hmm. Alkene. Because we want to form the more stable carbocation, but both carbons are equally substituted. And let's see.
Wouldn't it be the one on the left one? Because it could do a methyl shift, right?
Yeah, I was thinking of like this one is the more stable carbocation, but the key doesn't match up with that. Like I was thinking like we could do this, form a carbocation here, and it wasn't if that's carbocation, we could do a methyl shift like that. But like the key doesn't match up with this, so I'm not too sure like what's going on here. Right. Because once we have to do that methyl shift, which is this blue methyl here, we have a more stable carbocation here, which is at the tertiary position. And the Br minus comes back to attack that carbocation to give us this product here. But the key says something else. It says like, this is the answer here. Where they just attacked this carbocation right away without the methyl shift. I'm not too sure why.
Yeah, that's what I was wondering about. It's like I'm not sure the keys like not matching up. And like
Yeah.
I wasn't sure in these types of situations if we could make like metal shifts.
Let's see. Maybe this is a Leaven's kind of thing, like where since it's in cold conditions, we want to form the kinetic product, which means the very first product that gets formed, which is this one here without the methyl shift, because this methyl shift reaction here takes time, which I think requires a little bit more heat or in room temp. But since we're in cold conditions, we want to form the one that gets formed first, which is probably this intermediate here, which leads to that product without the methyl shift. But I think that's a Leaven's thing. Like Leaven's would specify that in her class.
Oh, all right. And then there's like there's two more answers to it. There's a
Yeah.
the key, it says there's a 3,4 dibromo.
Right. So that's
It-
with this let's see, this thing right here, where let's see. Hmm. Oh, I see. So since Leavens, I think she doesn't like want the methyl shift or hydride shift to happen because that is an extra step that takes time to react. But we don't have that time because we are in cold conditions. We are looking for the first thing that gets formed. So instead of having this carbon here grab the hydrogen, let's say we used this carbon here to grab the hydrogen and kick out the Br, we are going to get this carbocation instead, which is the same stability as the other carbocation because it is still secondary without the hydride shift. And then the Br minus is just going to come in and attack that carbocation and give us this other product here. Right. That product
Oh,
and
okay.
this product here. They both come from secondary carbocations with no metal shift because we don't have that time to do metal shift because we are in cold conditions. But I think that's more of a Leibniz thing. Like I wouldn't worry about that for Pascal. The other product that she said was missing in the key was 3,4-dibromo 2,2-dimethylhexane, 2, 3, 4, 5, 6, 3, 4-dibromo 2-dimethyl 1, 2, 1, 2, 3, BR. This is the other product here that was missing in the key. And this product came from this one here. Because you know how we got these first two products from this alkene here, where the BR either attached to this carbon or that carbon right there. If we reacted with that carbon, it gave us straight to that product there. If we reacted with this right carbon, it went to oh wait, no. I meant if we react with this left carbon here, it went straight to this product here. If we react with this right carbon, it went straight to that product there.
Uh-huh.
Right. It's the same thing for this alkene here. If we react it with, let's say, this right carbon there, it's gonna go straight to this same exact product at the bottom here, where the bromine is attached there. They
Oh,
have the
okay.
same connectivity. But the other product is the bromine could attach here as well.
Okay.
Right. So think of it like since we have excess HBr, we're gonna attach Br on both carbons because they are both equally substituted. And in this case, we don't worry. Let me put a note here. Do not worry about hydride or methyl shift because cold conditions,
Okay.
which means
Oh,
we are looking for the kinetic product, the very first thing that gets formed. We don't have that time for the shift rearrangement.
all right. So basically, in these types of questions, right? You just you'd first find the most stable like rearrangement, which was the first one.
Mm-hmm.
And then after that, since you'd probably get you're gonna get two different positions where they could be at, right?
Mm-hmm.
And then since it's in excess, you would want to do practically the same, right? And find the most stable one. But in this case situation, since they're both equally substituted, we just find as much possibilities as we can, right?
Yeah, that's right. Right. Since they're both equally substituted, we get different possibilities here. Where some of the possibilities, like let's say this one here that I'm highlighting red and this one there that I'm highlighting red, gives the exact same product if we put bromines there, which is
All right.
this one right there.
All right.
Which is why we don't get 4 different ones. Like it seems like we want 4 different ones because we have like 4 different carbons to react it with, but 2 of them gives the exact same product.
All right. That makes more sense.
Yeah.
Okay,
That's
thank you.
interesting. Like I've never seen that kind of problem before.
Yeah. Also, I have one more question.
Yeah.
It's for you on the same on the same theme. Letter U.
Letter U.
Yeah.
Let me see. Letter U. Rest to U. Okay. Rest to U. Okay. This is gonna be some interesting electrocyclic reaction. React this with heat. Okay, let me try doing this without looking at the key blindly, because let's see how I would do this. I know this is gonna be some kind of ring closing because I have heat and I have like some kind of system that wants to close. Like we could imagine the arrows like this right here. Right? Do these arrows make sense like that?
Yeah.
Right. So once I do that, I'm gonna get this template right here. I think let's see if this is right. Let's say that this highlighted portion here is gonna be this highlighted portion right there. This methyl group here is on an sp2 carbon, which is still gonna be on an sp2 carbon, which is gonna stay flat and planar, no wedge, no dash. Right, where we see now these groups here, these 3 groups were sp2, but now they're on sp3. So they're going to be either wedge or dash. We don't know that yet. We have to do the like thumb rule, like conrotatory, disrotatory kind of trick, where we have 3 pairs of electrons, which is an odd pair under heat. And let's see, I don't have the table memorized, so let me see if this is conrotatory or disrotatory.
I think it's CDDC. So
Uh-huh.
if it's odd,
Odd
it
pair.
should be disrotatory, maybe.
Disrotatory. Okay. Let's just go with disrotatory, and we'll see. But actually, let's just check just in case.
I think it's
It's this.
Disrotatory. Okay. Let's stick with disrotatory. Now, let's see. What is going on? Okay. This is an interesting one because you know how we're used to like only 2 groups rotating, right? But this time we have 3 different groups. We have this group, that group, and this group as well. Right? So
Mhm.
let's just focus on 2 groups first and then the other 2 groups. Let's say let's do these 2 groups first right here. Right. You notice how they are going like away from each other, like one is going up and then the other one is
Yeah.
going like that other direction. So let's start our thumbs like this. One is going to go left, one is going to go right. If this is disrotatory, I'm going to say this is going to go clockwise. This has to go counterclockwise, which is this way, where I see now that they are both going in the same direction, cis, right? So they both have to be wedge or dash. In this case, I'm just going to choose wedge, but they could be dash as well, which is the enantiomer version of it. Let's say that. Now let's focus on these 2 right here. These 2 are also facing away from each other because we see this one is going up, this one is going down like that. There are trans to each other, so we're gonna start our thumbs trans to each other as well. One thumb is gonna go to the left, the other thumb is gonna go to the right, trans to each other. This is disrotatory, so it's the exact same rotation as we did earlier. So they're gonna be cis to each other as well.
Okay.
Right.
Oh wait, that makes sense.
Right. Yeah. Nice. Is this the answer? Wait, let me check.
Yeah, the answer is that's the answer.
Oh, okay, nice. In this case, this was a weird one because we're used to only like 2 groups with the thumbs, but this case we had like 3 different groups to do the thing with. So we had to do the thumb rule 2 times.
Okay, so you would do the thumb one on the top part or the one like connecting straight to the left, the top left, and then you do it, those 3.
Yeah, we focus on these 2 first, which are like, you know how they are like kind of adjacent to each other, like where they are. Yeah, we can only do the thumb rule where they are like adjacent to each other. These groups here are way too far away, so we can do the thumb rule with these 2 groups here. They're way too far away.
Okay.
But we can do the thumb rule with this group and that group right there, which are adjacent to each other like that.
All right. That makes more sense. Thank you so much.
Yeah, no problem. Dang.
Oh, I have a quick question on this one.
Yeah.
Is this a electrocyclic reaction or like a Diene-Alder's reaction?
This is an electrocyclic ring closing reaction. Ring closing. Right.
How do you like know it's ring closing? Because I thought at first it was like Diels-Alder.
Oh yeah. I just realized this is a diene here and this is a dienophile.
Yeah.
Wait. Let's try that. Let's try this might be an intramolecular Diels-Alder reaction.
Oh, well, yeah, I mean you made it look like it made sense. I was like, all right, I guess so.
Yeah, because like you know how this is the same like template for the exact product for the Diels-Alder, like the cyclohexene here. It works though, so if it works, it works. But let's try the Diels-Alder way. That thing I forgot about that. Right. So we know this is the diene portion, and this is the dienophile portion. This is the EDG, that's the EDG. When we have the EDGs like that, you know, where would be our partial negative charge? Which carbon on the diene? Like, let's say this is 1, 2, 3, 4. a way to figure that out is imagine there are lone pairs on those atoms, but even though there are no lone pairs there, imagine there are lone pairs there. And when you do resonance, where would the negative charge end up at?
To 4.
Yeah, 4. That's right. Because this could go down here, push that down there, give that negative charge, or this can go down here, push that down there, give that carbon 4 a negative charge. We know this dienophile here has this EWG right here, which is that carbonyl carbon. When we do resonance like that, we know there's gonna be a positive charge on this top carbon right here. The charges did not align. What is going to happen? Can I
So
flip
is
this?
it like not possible because you can't rotate it?
Yeah, we can't flip it upside down because of this ring right here.
Okay.
But let's see here.
Wait, but I thought there would be a partial positive charge at the carbonyl.
Yeah, there is a partial positive charge at the carbonyl, but when we do resonance with that dienophile there, it's gonna look something like this here. Right. Where there's a full positive charge on that carbon right there. Right. So that's why there's a bigger partial positive charge on this carbon than this carbon. But in this case, this is a weird example where we can't flip the dienophile upside down. In this case, usually we would flip it upside down to get the product, but we're forced to stick with this product here. We can't flip it. We have to do it like that, right? So this is a weird example where even though the charges are misaligned, we cannot flip the dienophile, which is the one I usually flip, upside down because it is part of the diene structure. Right? Yeah, we can't flip this upside down, right? Can we? No, we cannot. Yeah, we can't do that. So it's forced to just go with that right there. Which this is still sp2. This right here, let's draw the pocket between the diene and the dienophile, which is that pocket right there. This is an outgroup where we know that outgroup has to be cis to the EWG, which is this EWG right here. So that's cis to the EWG like that. Right. Since this EWG is also cis to this like R group here, that R group would also have to be cis to that EWG, where those two groups here are connected with another ring like that. Right. Which is the exact same thing as this right here.
All right.
Mhm.
That makes sense.
Yeah.
Thank you so much.
Yeah, no problem. Mhm.
Where did the double bond of the dienophile go?
The double bond, this one or this one here?
The dienophile.
Oh, the dienophile. The double bond of the dienophile, I moved it to here. It is now that bond right there. That double bond made a bond between carbons 4 and 5. 1, 2, 3, 4, 5, 6. Right. This double bond here, I drew an arrow to make a new bond between 4 and 5 like that.
Okay.
Yeah. It doesn't have to be like that. It could have been the other way as well. Like it could have made a double bond between 1 and 6 if I drew the arrows like this. Yeah. It could be like the other way. Yeah. Mhm.
So like in this case, it doesn't matter if you see it like a electrocyclic reaction or a Diels-Alder reaction. It just gets you the same product.
Yeah, because a Diels-Alder reaction is a type of electrocyclic reaction. But
Oh,
it is more complicated because of the regiochemistry. Like if there's EDGs, EWGs, you have to make sure the charges are aligned. But in this specific example here, we can't flip this even though they are not aligned because it's weird. Like it's connected to each other. It's intramolecular. So it's forced to react with each other. Another way to think about it is that intramolecular reactions happen way faster than intermolecular reactions. Right? We know this is an intramolecular reaction because like the things reacting are in the same molecule with each other. So that allows the reaction to happen without the charges being aligned. Because intramolecular reactions are way more favored than intermolecular reactions. So this is just a weird example of Diels-Alder here. Like even though the charges do not align, we can't flip it. So we're just forced to get to this product here. Another way you can think about it is like this electrocyclic ring closing here. But for other Diels-Alder reactions, right? Don't think of it like electrocyclic ring closing because that will not give you the right answer all the time. Because in most cases, which are the cases that I think are gonna be on your exam, you have to actually flip the dienophile to match up the charges. In this case, we couldn't flip the dienophile. So this is just a weird example here for leave-ins. Right. So let's do more Diels-Alder reactions to make to reinforce that concept. Like let's say we have this here. Or any other questions before we go on with this worksheet? Okay, let's do this problem here. Okay, so in this case, it is easy to see where our diene is, which is this part, and where our dienophile is, which is this part. Let's make the pocket between the diene and the dienophile. Let's number this 1, 2, 3, 4, 5, 6. We know that this R group here is an EDG. And that would create a partial negative charge on carbon 4 because imagine I had a lone pair of electrons. It doesn't, but imagine it did. It's gonna make a double bond there, push that double bond there, and create a lone pair of electrons on that carbon right there. Right.
Ryan, sorry.
Yeah.
Could you go over how you decipher which one is an EDG or EWG?
Yeah. So let's go over that concept, EDG versus EWG. So I give a lot of examples with that. EDGs versus EWGs. So an EDG is gonna think of it like this. If the atom, okay, wait, before that, for both of these groups, only look at the very first, everything else is a distraction, atom directly attached to the system. And that is important because I'll show you examples where some people get confused and they switch up the EDG versus the EWG. Right. So an EDG, you can think of it as if the atom has a lone pair of electrons, it's an EDG because it has lone pairs of electrons to donate into the system. If it is an R group, like a random hydrocarbon chain, like a methyl, ethyl, propyl, butyl, isopropyl, sec-butyl, tert-butyl, that is an EDG through induction. Right. Another thing is that if the very first atom directly attached to the system, the charge is partially negative or fully negative. Right. For EWG, you're gonna see if the atom is, let's say, has a pi bond, which is a double bond. It's most likely a carbon, like it could be carboxylic acid, it could be aldehyde, it could be a ketone. Most likely, like the common cases are esters, like OR. It could be OME, carbonyl, OME. It could be OET, right? When you see ME, just think of that as methyl, CH3. If you see ET, think of that as ethyl, CH2, CH3. It's just an ester group, right? But those are distractions because, like I said in the very beginning, we only look at the very, very first atom attached to the system, which is this carbonyl carbon here, the carbon that is double bonded to the oxygen. We know that carbon that is double bonded to the oxygen is partially positive because it is less electronegative than the oxygen. And because it is partially positive, it wants to withdraw electrons. It wants to gain more electrons, which is why it's an EWG. Right. Another thing is if you see any halogen, like chlorine, bromine, iodine, because they are very electronegative. And this is also through induction. They withdraw electrons through induction because they are very electronegative. And like we said earlier, the very first atom has to be partially positive or fully positive. So let's look at some examples. But I kind of give a lot of examples for the EWG already. Right. Where all of these examples are examples of a carbon with a pi bond or carbon that is double bonded like that. Right. Let's see. For EDG, you could see OR, which is like you could see OMe, OCH3, because we know that atom oxygen is partially negative and has at least one lone pair of electrons. You could also see NH2, NRH, NR2. You could see, let's say, okay, now this is the tricky part here. Wait, let me say like methyl group, ethyl group, isopropyl, tritbutyl, like any R group. These are random R groups. They are EDGs as well. For EWGs, it's gonna be all of this here for the carbonyl. Chlorine, bromine, iodine, and this is the important thing here. NO2. This NO2 is different than NH2. NH2 is an EDG because it has a lone pair of electrons and is partially negative. NO2 here, I'm going to draw out the whole Lewis structure to show why this is an EWG. This is NO2 right here. We see that the very, very first atom directly attached to the whatever the system is this nitrogen right here that has a full positive charge right there with no lone pairs of electrons. This nitrogen has no lone pairs of electrons because it already has 4 bonds. It already has the octet rule, but because it has 4 bonds, it has the full positive charge. And because it has the full positive charge, it is the EWG. So that's an important distinction you have to make. Like NH2 is an EDG, NO2 is an EWG. Right, so let me make that note. This is an EDG. This NO2 is an EWG. Okay. Let me give you some like comparison problems. Let's say we have something like this versus something like this. Okay. Which one is your EDG? Which one is your EWG?
I'm guessing it's the one on the EDG is the one on the left.
Right. So remember how we have to look at the very, very first atom attached to the system? The very first atom attached to this left one here is that carbon right there. What is the partial charge of that carbon?
Isn't it positive?
Yeah, partial positive. And did you say that was the EDG or EWG?
Is it the EDG?
Oh, wait. So that atom there has no electrons to donate. And since that atom is partial positive, it wants to gain electrons. So this is the
It's an
EWG, right? The very first atom on the right is that oxygen right there. Where what is the partial charge of this oxygen here with 2 lone pairs of electrons?
It's negative, partially
Yeah.
negative.
And since it has 2 lone pairs of electrons, it can donate electrons. That is an EDG.
Okay, I get it now.
Right. Okay. So do you get like this part here now, like where how that methyl group is the EDG? Because we said any random hydrocarbon chain, hydrocarbon is an EDG through induction, which is this methyl group there, which is a random R group, EDG.
So any random R group is just an EDG then, if you see them.
Yeah, any random R group. It doesn't have to be a methyl group. It could be an ethyl group or an isopropyl group. Any random hydrocarbon chain.
Okay, thank you.
Yeah, no problem. What is this group here attached to the dienophile? What is the very first atom attached to this dienophile? The very, very first atom directly attached to the dienophile.
Are you talking about, is that like the EWG?
Yeah, right. Because the very first atom attached to the dienophile is that carbonyl-carbon that is partially positive. And because that is partially positive, this is the EWG. Like that. That whole thing, this whole thing here is the EWG. Right. Nice. Okay. Now let's see where the charges are going to be at. Since this is the EWG, right? Do you know where the partial positive charge is going to be on the dienophile? Based on the EWG on this carbon here, like, would it be on this carbon here or this carbon here? Like, if we drew out the resonance structure of this.
Would it be on the first dot that you drew?
Right. So it looks like it's the first one because it's closer to the positive charge one here, right? But
Yeah.
it's actually going to be on the bottom one here because when we draw its resonance structure, it's going to look something like this. I'm going to move that double bond to make a double bond there and pop this double bond onto that oxygen right there. This gives us this resonance structure here. Does that make sense so far? Like how I got that resonance structure with
Yeah,
these
that makes
arrows?
sense.
Right. Yeah, you know how in this resonance structure, we could clearly see that full positive charge on that carbon right there? Like there's
Yeah.
no positive charge on this carbon right here. The one that you said originally, the first one, there's no positive charge there.
Okay.
Right. But there is a full positive charge on this carbon here. Which is why this bottom carbon here has the partial positive charge instead of this carbon here, even though this carbon is closer to the positive charge. So that's a tricky thing, right? Because of resonance, this carbon here has a bigger positive charge than this carbon here. Does that make sense so far?
Yeah, that makes sense. Thank you.
Yeah, no problem. Where now, since the charges do align from the diene and dienophile, we can go through with the whole mechanism arrows and give this template product, right? Where let's say this is 1, 2, 3, 4, 5, 6. Now, this methyl group was on an sp2 carbon, but now it's on an sp3 carbon. This EWG was on an sp2 carbon, now it's on an sp3 carbon. To tell like what they are in relation to each other, this is going to be the endo rule here. So here's a shortcut for the endo rule. Think of octi, or it kind of sounds like a octopus, right? Where the out group cis to EWG, in group trans to EWG. And I'll show you what out group and in group is, but octi, the O is out group, the C is cis. Out group, cis to EWG. The I is in group trans to EWG. So let's say we have a diene here and a dienophile here. We know that this is the pocket between them that's going to react because that's the new bond that's going to get formed. And there could be groups on these dienes and dienophiles. These are outgroups because these groups are facing outwards, away from the pocket. These are in groups because they are facing inwards, towards the pocket, in the pocket. And the dienophile, like it usually has an electron withdrawing group, right? Like that. And since we said, let's say this is 1, 2, 3, 4, 5, 6, and react that with heat, we are going to get this diene, no, this Diels-Alder product, where this is 1, 2, 3, 4, 5, 6. We said the outgroup is cis to the EWG, octi, cis. So let's make the outgroup a dash. It could be a wedge as well, but I usually see these as dashes. You just put plus enantiomer at the end, right? Since the outgroup is a dash, we want the EWG also to be a dash because outgroup cis to EWG. We want them on the same side. That makes the in-group wedge because the in-group is trans to the EWG, like that. Okay. Does that make sense so far?
Yeah.
Right. So let's look at this example here. Is this EDG an outgroup or an in-group?
It's an outgroup.
Yeah, right. It's an outgroup. So does that make it cis or trans to this EWG here?
It's cis.
Yeah, it's cis. So that's how we tell the stereochemistry between the outgroup and EWG. So let's make this a dash and this a dash as well, which is OCH3. And we could say plus enantiomer because this could have been a wedge and that could have been a wedge as well, where they are both cis, like that. Okay. Yeah. Is this Diels-Alder stuff making more sense with the regio selectivity, stereo selectivity stuff?
Yeah, that makes more sense. Is there gonna be like harder problems that are like the ones that
Yeah.
twist?
Yeah, the ones that twist, the ones that where the charges do not align, where to flip the dienophile, the ones where it's very hard to locate the diene and dienophile, way to rotate it, and stuff like that. Like this is like relatively like the simple ones. But then like let's build on the difficulty, right? Let's now make it so that the charges do not align and we have to flip the dienophile. So let's say we have and I'm going to include a group on this carbon here as well. And we have okay, tell me how you would go about this problem. What would you do first?
First I would connect, or I would like look at the charges and see if it connects first.
Right. So let's look at the charges. Let's look at the diene here. Where would be the partial negative charge on that diene? Let's say this is 1, 2, 3, 4. And this is going to be 5 and 6.
Would the negative charge be on the 1?
Yeah, that's right. It would be on the 1. It's not going to be on the 4, even though it's the closest to the EDG, the strong EDG here, because we know when we do resonance, push that lone pair to make a double bond there, push this double bond here, push that double bond to make a lone pair there. There's a full negative charge on carbon 1 right there when we look at its resonance structure, right? Which is why there's a partial negative charge on 1 right there. Now, where would be the partial positive charge on the dienophile here?
It'd be on the 5.
Yeah, it would be on the 5 because when we draw its resonance structure, NO2 looks something like this. The positive charge would be on that carbon 5 right there. Right. Now let's see the pocket between the diene and the dienophile. right? We notice that the charges here do not align. Like the negative charge is on top, the positive charge is on bottom. So what do you think we have to do to fix this problem here?
You'd have to twist the Diene file.
Yeah, rotate that upside down, right? If you went straight for the product right away, like this, let's say NH2, and this is NO2, this is going to be a minor product, right? We don't want that because the charges did not align. So we would have to rotate that upside down, make the NO2 down here, where we see the partial positive charges now on top with the negative charge. And since now they do align, we can do the regular Diels-Alder with heat. And we know this NH2 here is an out group because it is facing outward, away from the pocket. And based on the Endo rule, we said the out group is cis to the EWG. So if I made this out group a dash, the NO2 would also have to be a dash because we said out group cis to EWG. It could be a wedge as well, which is the enantiomer plus the enantiomer. This methyl group right here was flat because it's an sp2 carbon. It remains flat and planar because it's still an sp2 orbital. So these two carbons right here always remain sp2 from the diene. So any groups on those two carbons always stay flat.
This might sound stupid. So for the Diene file, it's always attached to the EWG, or is that like not the case?
Oh, the diene file? Yeah.
Yeah.
So that's not a dumb question because that is what makes the reaction faster. Because for Diels-Alder, right? This is a conceptual question that is a high likely chance that it's going to be on the vocab or conceptual multiple choice question. He might ask like what speeds up the reaction. We know a diene is going to react with a dienophile. And that is always going to make some kind of cyclohexene adduct. Right. Because our product for Diels-Alder is always this cyclohexene here with like other decorations on it. Think of your diene as your nucleophile in the reaction and your dienophile as your electrophile in that reaction, right? You know how nucleophiles, they are negative charges, they want negative charges to attack the positive charge electrophiles. The reaction rate will increase if you have EDG on diene and EWG on dienophile. This is because the EDGs makes the diene more negative charge. It donates electrons into the diene, making it more negative, making it a stronger nucleophile. The EWG steals or withdraws electrons from the dienophile, making that the dienophile more positive since it's losing electrons. And because it is becoming more positive, it's becoming a stronger or better electrophile, which is what we want because the dienophile is the electrophile in this reaction. So that's why it speeds up the reaction when the electron-withdrawing group is on the dienophile. If the EDG, like if it was reversed, right? Like if the EDG was on the dienophile and the EWG was on the diene, that would slow down the reaction. So that could be a conceptual question. Like you might ask, would this slow down or speed up the reaction? If there's an EWG on the diene and the EDG on the dienophile, that would slow down the reaction, right? Based on these concepts here.
That makes sense.
Another thing that speeds up the reaction rate is something like this, because the diene could either be in the S-cis configuration or the S-trans configuration. What? No, no, no. Yeah, that's the diene. The diene could be in the S-cis configuration, which is this one here, or the S-trans configuration. But for Diels-Alder, only the S-cis configuration reacts. The S-trans configuration does not react in Diels-Alder. Right. So the reaction rate will be faster if the diene is fixed, meaning that it's locked in a ring. It can't rotate back into the S-trans. So it could be like that. It could be like this. It could be something like that, where there's no way to rotate this single bond because it's locked in a ring. So no way to go back to the S trans configuration. So these fixed molecules here, fixed dienes, really speed up the reaction rate of the Diels-Alder. Right. But if you have S trans alkene, diene, you could rotate that single bond to go to the S cis diene. You cannot do that if it is, let's say, something like that, right? Now we can't rotate that bond because it's in a ring. So it's stuck at the S trans configuration. No reaction with this structure at all. Yeah, so these are like conceptual questions like the EDG and EWG on the diene dienophile. What speeds up the reaction? What slows the reaction? If it's fixed or not. Yeah, right. We went over regional selectivity where the charges align in the pocket. We went over stereoselectivity of the endo rule. Out group is cis to the EWG, in group is trans to the EWG. But now we just gotta apply all those things that we talked about into like different weird looking example problems. Which we're gonna do tomorrow during the review session. Right. Any other questions, or do you guys want to go over one more Diels-Alder reaction, like a tricky one?
We can go look at a tricky Diels-Alder.
Okay. Let's do a tricky one. Let's say we have okay. Let's try this one here. Right. Okay, what would you guys do first? Looking at this here.
Turn the single bonds.
Oh,
Like,
rotate the single
okay.
bond here?
Yeah.
Yeah, that's
Yeah.
right. Because this right here, we notice is our diene, but it's not in the right configuration. It is in the S trans configuration. So when we rotate that, this is how I rotate it. I keep everything on the top the same, and I'm gonna swap these two groups here. I'm gonna swap the isopropyl group with that alkene. So this top part stays the same. This is the single bond that I'm rotating right there. Now the alkene is there and the isopropyl group is here. Did that make sense? Like how I rotated, I just swapped these two groups right here.
Yeah, that makes sense.
Right. So now this is weird because our diene, which is in the S cis configuration now, is like facing in the weird direction. I'm gonna flip it like a page to give us this kind of configuration here. Like that. Where now this is our diene. And this is our dienophile right here. That double bond right there. It's like oriented really weirdly. But first, before I like rotate it into the structure here, I have to figure out where's our negative charge here. Where is going to be our partial negative charge on the diene? Carbons 1, 2, 3, or 4? dependent on this EDGs here.
Is it 1?
Oh, right. So it is not gonna be 1 because like it looks like it's the closest to the EDG, right? But remember how when we do resonance, like we donate the electrons down there, make a double bond, move the double bond down here, that pushes that double bond onto that carbon, giving that carbon a negative charge right there, right?
So
Oh,
it's 4. Okay.
yeah, so it's 4. That's right. That means that we want our dienophile, we want the positive charge on the bottom right there, right? But we have to figure out which carbon is our positive charge. Let's say this is 1 and 2. Where would be our positive charge dependent on this EWG here? Like think about the resonance structure here. Right. Like if we look at the resonance structure, let's say we move this double bond here because it's on an EWG that pushes this double bond onto the oxygen. Since this carbon is losing a bond, that carbon is having the positive charge right there. So our partial positive charge is going to be on carbon 2. Does that make sense?
Sorry, I like completely forgot about resonance, so I'm just like rereading it right now.
Oh, I see. Yeah,
fine.
let me write that down clearly for you here. Like that, like that, like that. O minus,
Okay,
double
that
bond,
makes sense. Yeah.
positive charge, where there's a positive charge here, which is, and then wait, but you get this resonance structure here, right? From the EDG, like what I got the negative charge like that, right?
Yeah,
We're pushing it down. Right. Since we know there's a positive charge on that carbon right there, that's the carbon that has the methyl group, which I'm gonna put the methyl group there. And I know that this methyl group is trans to that EWG, so I have to make that trans as well. The reason why I put the ketone up here and the methyl down there is because I know the positive charge is where the methyl group is. And that's why I want the positive charge to be at, because that aligns with the pocket charges. The negative charge is aligned with the positive charge. So let's do the regular arrows here. Let's draw in that template, cyclohexene. Okay, so what would be the stereochemistry of all of these groups here? Right. What would be the stereochemistry of this isopropyl group here? Would it be wedge, dash, flat?
Wouldn't it be flat?
Yeah, flat, because it stays on an sp2 carbon. Now, what is the relationship between this group and this group here? Like, are they cis or trans to each other?
Trans.
Right, so what is this group here? Is this an out group or an in group? Is it going away from the pocket or in to the pocket? Like this is the pocket right here. So this group here is gonna be an out group, right? Because remember when we went over the endo row, where is the endo row? Right here. We want the out group cis to the EWG. This is the out group here. This is the EWG here. So we want those groups to be cis to each other because out group cis to EWG. So let's make that a dash. That makes this group dash as well because we said that they are cis. Since that is dash, this methyl group is forced to become a wedge because that is trans to the EWG plus enantiomer. Final answer. Right. Where
Sorry, I'm confused about the methyl. Wouldn't it
Oh.
also be because it's also like an out group, so wouldn't it also be like cis with the rest of it?
Yeah, so when we talk about out and in groups, we only talk about the diene, which is this out and in group here. Like the out group is facing away from this pocket. The in group is facing in the
Oh,
pocket for the
so
diene.
you don't look at the dienophile at all for like the out and okay.
Yeah, you don't look at the dienophile at all for the out and in. You only look at the dienophile for where the EWG is,
Okay.
which is this EWG right here. And since that's the EWG, that has to be cis to the out group from the endo row, which is this cis right here. the other thing is just random. Uh, this methyl group is random, which is trans to the EWG here, which is why I have to make it trans. But if the methyl group was here instead, right? Then that would be dash because now they are cis to each other. Right. But it's not cis, it's trans, so I have to make it trans like that. Any questions on this Diels-Alder problem? Okay, so that is it. Tomorrow for the review session, I'm still preparing like the practice problems, practice midterm. We'll probably do more complicated Diels-Alder problems. Do you guys have any like topic suggestions you guys want to go over? Like what you guys are struggling with the most? So we could focus on that more for tomorrow's session on the content review.
I just don't know. It's too much.
It's too much.
Yeah.
You don't know which topics to look at.
Yeah, I don't
Yeah.
even know where to start at.
Yeah, Diels-Alder, in my opinion, is the hardest part of this midterm. Like everything else is easier. Like the thermodynamic, kinetic, NBS, benzene stuff is easier than this Diels-Alder stuff. Like this Diels-Alder stuff is the most confusing part.
Are we gonna
the
go
midterm.
over like the new stuff that he went over today as well?
Yes,
From-
that's gonna be for Thursday's session.
Okay.
When he
Gotcha.
goes over everything on Thursday as well.
And I also was confused. So I guess like the NMR stuff for benzene is that gonna be on the test? I was kind of confused when
I
Yeah.
think, yeah.
Yeah, it will be on a test with the ortho meta para stuff.
He just posted a practice midterm, so you can
Oh.
check.
Oh, he posted it? Okay, yeah. I'll check
Yeah.
that out as well. Nice. Okay. It's good. I thought he was gonna post one because when he taught 118A like some quarters ago, like last year, he didn't post a practice midterm for midterm 2. So I was like, is he gonna post one for this quarter? But luckily he did. Yeah. Okay.
All right. Thank you so much. I'll see you tomorrow then.
Yeah, I'll see you guys tomorrow. See
Yeah,
ya.
bye.
Bye.